Okay, this should be the last Chapter 5 video. We've just got a couple things to wrap up here. One is the idea of weightlessness, or how things moving around us can give the appearance of additional or less gravity. So typically when things are stationary, we've got a lady here in an elevator car that's not moving. The force she is experiencing due to gravity is equal to mass times gravity. So if we have this weight attached to a scale, it's being pulled down by gravity, mg. So the weight on it reads, what is it looking like, 20 on this scale here. So when the elevator car is slowing down or accelerating in the upward direction, let's say, then we have an additional force or apparent force acting on this weight. So the weight is still being pulled down with mg, but the floor of the elevator is accelerating up, which applies an additional force in the upward direction. And so we actually experience additional weight. It seems to feel like there's more weight because her weight is acting down, the elevator car is accelerating up, and so it's pushing against her with an apparent weight more than what it normally would be. And in the last case here, if the elevator car, if the cable were to break, the elevator car itself is accelerating down at the same rate that she is accelerating down, the same that this weight here is accelerating down. Since everything is accelerating at the same rate, it gives the sensation that there is no weight. So the scale actually reads 0 here. So when the car accelerates up, she feels heavier. When it accelerates down, she feels lighter. If it's in a complete free fall, she feels completely weightless. And it seems to me like her reaction here is a little understated, given the fact that the cable just snapped and she's falling presumably to her death. That's how the illustrator felt she would react, apparently. All right, so weightlessness can be experienced on Earth if you're falling through the air for a short period of time. Astronauts can train on airplanes that travel up and down in a parabolic motion, and when the airplane is on the downhill descent, you have what feels like a period of zero gravity. It's just some weightlessness. I'll post some videos on Blackboard that I think are pretty cool that shows this this type of weightlessness on a plane. And that brings us to one of our last topics of this chapter, which is Kepler's laws of planetary motion. So planets orbit the sun not in a circular orbit, but in an elliptical orbit. So it goes around here, and an ellipse, if you remember from geometry, has two focuses or foci. So an ellipse has two foci. Two of them are along the larger major axis, and then that's perpendicular to the minor axis. So the distance between a planet and the sun varies at different points throughout its orbit. So sometimes it's closer to the sun. At other times, it is farther away. When it's over here, the distance is larger. So although the distance between a planet and the sun may change at various points throughout its orbit, if we take the average of these distances, we get the mean distance or average distance from a planet to the sun. Okay, and let's move on here. So at any 2 points in time, if we look at these shaded areas here, like taking slices of pizza out of an elliptical shaped pizza, if these two the time between point 1 and point 2, if that's equal to the same amount of time from point 3 to point 4, then the shaded areas are equal to each other. So although it seems as if this is a larger distance, which it is, it takes a longer distance to travel, that means that the planet is moving faster here than it is out here to travel a smaller distance. But the areas remain equal. So what this all means to us, how we're going to apply this knowledge, is in looking at the various planets and their mean distance to the sun. So that's what S is. That's the mean distance to the sun. So the average distance between the planet and the sun, which it varies slightly from at different points in the year, so we have to average them. And T being the period measured in Earth years. Well, the chart here gives it measured in Earth years. So on Earth, a year is 1 Earth year, obviously. Venus goes around the sun a lot faster. It only takes 0.615 of 1 Earth year for Venus to go all the way around. Mercury is going around Earth very quickly. And if we look further out here, Neptune, for instance, it takes 165 Earth years for Neptune to travel around the sun just one time. Okay, so if we take these mean distances and cube them, divided by the period squared, that relationship remains constant. So, for instance, the mean distance to the sun for the Earth and the period of an Earth is equal to the mean distance from Mars to the sun cubed divided by the period of Mars squared. So Mars over Mars, Earth over Earth. The relationship between these two things are constant and they're equal to each other. So let's take that knowledge and apply it to this question here. If a year on Mars is 670 Earth days, and the mean distance from Mars, we want to determine the mean distance from Mars to the sun based on what we know about the Earth. We know that the mean distance from the Earth to the sun is 149.6 times 10 to the 6 kilometers. And so if 687 Earth days, if we divide that by 365 days per year on Earth, we get 1.88 Earth years. So a year on Mars is 1.88 Earth years. So what we want to do is we want to determine the distance. So let's use Kepler's ratio here, his law that says the distance from Earth cubed over the period of Earth squared is equal to the distance of Mars cubed over the period of Mars squared. And so the mean distance for Earth, the distance from Earth to the sun, is 149.6 times 10 to the 6th kilometers. And the period on Earth, 1 Earth year is 1.00 squared, equals the mean distance of Mars, that's what we want to find, cubed, divided by the period of Mars is 1.88 Earth years, and then we have to square that. So S, which is the distance, the average mean distance from Mars to the Sun, which is what we're trying to find, is going to be 149.6 times 10 to the 6th times 1.88 squared divided by 1.00 squared. Oh, and cube root all of that. I almost forgot the cube root. So we calculate that. We should find that S is 228 times 10 to the 6th kilometers. That's the mean distance from Mars to Earth, found using Kepler's laws of planetary motion. Okay, so to wrap up this chapter, we want to look at the fundamental forces at work in our universe. The 4 fundamental forces are gravity. So we talked quite a bit about gravity in this chapter. Second one is electromagnetism. And then the third and fourth are found within the nucleus of an atom. We've got weak nuclear forces and strong nuclear forces. So every force in the universe affects or can be categorized as one of these 4 types of forces. So most forces that we deal with on a day-to-day basis, pushes, pulls, objects coming into contact with each other, are actually a form of electromagnetic forces. So, or either that or gravity. So gravity acts on us. Every other force that we come in contact with, typically, other than gravitational forces, are due to electromagnetic forces acting at the atomic level. So when, for instance, you stand on the floor, and the floor pushes back on you. What are the forces at work? It's actually electromagnetic forces between the atoms in the floor and the atoms in you. So just kind of an interesting thing to note here, that all of the forces we talk about are either 1, gravity, or 2, electromagnetic. All the other forces are atomic forces, which don't really affect us on a day-to-day basis. So that's it. That's it for Chapter 5. I'll make some videos now for Chapter 6.